Welcome to another late night video on factoring. This one is called Factoring Completely. And to give you an idea of what it means to factor completely, we got to talk a little bit about what this word factor means. So just like in English, a word like slide can mean a slide at a playground, which is a noun, or it can mean to slide on the ice, which is a verb. Factor or factoring can be used in two different forms. It can be used as a verb. If I say factor, a particular expression, I'm asking you to express it as multiplication. So when you're all done, it's something times something. If I talk about the noun factor, it means the quantities themselves that are involved in the multiplication. So something like this, we had learned how to factor in the last factoring video. It was a difference of two squares, and we were able to rewrite it like this because x times x is x squared, 2 times 2 is 4, and then you put one of each sign so you don't have a middle term. So we factored it, the verb, and then the factors are, this is one factor and this is the other factor. And what makes these be factors is they are the quantities that are involved in the multiplication in our final factored form. So factoring completely means that when we factor, that none of the factors can be further factored. In other words, if this was a standalone problem and we were able to factor it further, we should. You all probably remember using like prime number trees way back. So if somebody gave you this 50 and they said do the prime factorization, you probably did 2 times 25, and then you looked at each of the two factors and you said, I think that can be factored further. So you wrote 2 times, and then you rewrote this as 5 times 5. So that was an example of a factor that can be further factored. So we're doing that sort of thing. We're not making prime factorization trees here, but we're doing a little bit of the same thing in that we're going to examine each factor to see if it can be further broken down. So let me grab my and let me put something like, here's my first example, something like 3x squared minus 300. So 3x squared minus 300. The first method of factoring we learned was looking for a greatest common factor. So we should still continue to look for that pretty much every time we're asked to factor something. So if you remember right, when we were factoring out a greatest common factor, you were looking to see if any number went into both terms, and in this case 3 would, and we were looking to see if there were x's that were in this case, because x is there, if there are x's in all terms, and there was not. So we drew one set of parentheses, and the common factor went out in front. So this is the one type of factoring where you use just a single set of parentheses and you put the greatest common factor out in front. So 3 times x squared is where the 3x squared will come from, and the 3 times the negative 100 is where the negative 300 will come from. So that is now technically factored. However, me included, most of the time when a teacher asks you to factor, they really do mean factor completely. So we are basically breaking down our factors until no factor can be further broken down. So my factors, now I'm using the noun, this is one little itty bitty factor, and this is the other factor, because these are the two quantities that are multiplying each other. Now something like 3, even if that were a number like 10, we wouldn't be breaking it down. It's just a number term, it's a single term. But this 2-term thing here in parentheses, does that look familiar? Does that look like something that we maybe have factored before? That is a difference of 2 squares. So the 3 isn't going anywhere, but I'm finding a better way to write x squared minus 100. So I'm kind of just not looking at the 3 and I'm focusing on this and rewriting this in a more factored form. So what times itself gives me x squared? What times itself gives you 100? And then if it's a difference of 2 squares, you just put one plus sign and one minus sign, doesn't matter the order. And then this right here would all multiply out to be equal to the original. Now this is why you have to bring down the 3. If you didn't bring down the 3, this would only come up equal to x squared minus 100, which was not equal to the original problem. So the 3 is needed to preserve the size of what you were given. Okay, so that would be your first example. Take a screenshot if you want, or hopefully you put this in your notes, because we're about ready to start another example. Okay, so here's a second example. Remember this last problem we did, we took out a 3 first, but there were not x's in both terms. Here, see how far you can get before we get to the doing of this. 2x to the 4th minus 18x squared. Okay, so looking at this, it's got 2 terms. A couple of classes ago we learned how to see if there was a greatest common factor, and we always start there. Seems like the earlier we learned a certain type of factoring, that probably is the order we should check for things in. So looking at this right here, I look and see if there's something that goes into 2 and goes into 18 evenly with no remainder. And the largest number that goes into both is 2. And are there also x's in each term? Well, there's x's here and there's x's here. So we can take out some x's. And if you remember right, when you're trying to decide how many x's to take out, you know that the biggest exponent you can put here has to make sense with what you have, and it always ends up being the smallest exponent you see. It's not bigger than that, because if I were to distribute, say, x to the 3rd, why wouldn't there be at least 3 multipliers of x there? So 2x squared times what would give me 2x to the 4th? Well, we already have the 2, but we need a couple more factors of x. So that times that gives me that, because I'm going to add the exponents and I want them to add to a 4. Then this times what gives me this? Well, the 2 needs to multiply by a negative 9 to get a negative 18. And we already have x squared, so I don't want more x's here, because then I'll have to add the exponents. But I only want x squared. It's going to get the x squared just from that. So there we are. So we have factored it technically. It's written as a product, this times this. Here's one factor, here's the other factor. Well, with that in mind, we take a look at this and we say, okay, does that fit any type of factoring? See, there's not going to be a common factor anymore because we just took it out. However, if you hadn't noticed the 2 was common, then you might still have a common factor here, and that's your hint that you didn't find the greatest common factor. Same thing with the x's. If you took out the 2, but you didn't get all the x's, you'll still have some common to both terms. So at that stage, this is a difference of 2 squares. So I know how to write that differently. X times x is x squared. 3 times 3 is 9, and put one of each sign. Now, is this my final answer? Actually, if I multiply this out, it comes out to this, not to the original problem. That's why you have to bring down any earlier factors you found. Okay, so if I took this and I got x squared minus 9 and then multiplied it by that, that would be equivalent to the original. So this is now considered factored completely. So if your teacher says factor this, they probably mean for you to do it completely. Okay, so I just have one more problem. This was example 2, by the way. Take a screenshot if you'd like. All right, one last problem. You all know how to take a screenshot, right? On an iPad or on a phone or whatever. You hit the home key and the power button at the same time. You have to be pretty exact too, because if you mistime it and don't hit them exactly at the same time, it does shut off your device most of the time. So let's look at example 3. And let's say it's going to be 9x squared. No, I'm going to make that be to the 3rd power. Minus, let's have it be 900x. So how would we go about starting this problem? Is there a greatest common factor? Go ahead and try starting this on your own. You think there's something common to both terms? If you do, set up one single set of parentheses. You might notice that there's a 9 common to both terms. With that, you can put a 9 out front. But you might not notice that there are x's common to each term. There are, and there really should be some x's here. But I just want to show you, if you accidentally don't get everything that's common, this is what happens. 9 times x cubed is 9x cubed. 9 times negative, and that's going to be 100x. And that times that does give me that. So multiplying the 9 through does equal my original. So it is factored. It's just not completely factored. So ideally what you want to do is look at both factors. The number, if it is just a single term thing, a single term out in front, you're going to always just leave it there. We're not going to break it down any further. But this thing right here, do you see how there's still x's common to both terms? The reason there are x's still there in each term is because I didn't notice that they were part of the common factor. So let's say I focus on this and I try to rewrite that. And I see that, oh, there's still an x in each term. I would end up with x squared minus 100. X times that is that. X times that is that. And the 9 hasn't gone anywhere. So you see how you end up with a 9x out front, just as if we had noticed from the beginning that there was a 9 and an x, both common to each term. So the 9 and the x will rejoin each other out in front, even if you have to do it in a couple of stages. So, and we're done here, or no? Hopefully you noticed, here's a single term. That doesn't break down further. It just stays as it is. But this two-termed thing, that's a difference of 2 squares. So you have yourself your x plus 10 and your x minus 10. And I write this because that times itself gives you that times itself gives you that, and that ends up being a different sign if you put a plus and a minus. So hopefully this video has been helpful. Actually, one last thing I want to mention. 3x squared plus 5. if I gave you this and I said factor this, you try our two techniques of factoring on it. So here, if there's anything common, do you know of any number that goes evenly into 3 and 5 other than a 1? There isn't one. So we aren't going to have a common factor that involves a number. Are there x's in both terms? No, there are not. So what that means is this is not going to factor by the greatest common factor method. Anyway, so now I see, is it a difference of 2 squares? Well, right away it's not even a difference. So it's failing that aspect. So for now, we're going to write does not factor. DNF means does not factor. And this is what you're going to write anytime that something doesn't factor by either a requested method or if you're just asked to factor in general. So that would be what you'd write right there. And it's just a short, you can write that out, can't be done, doesn't factor. The key is you would leave the answer like this and it would stay that way. Not all things come from multiplication, so therefore not all things are reversible back to something that was originally multiplied. I will say one word of caution. It is true that that doesn't factor, period. But there will be some things we learn later on that we won't know how to factor. We won't know the technique yet, but it actually is factorable, just not yet, based on what we've learned. So I hope that this video has been helpful to you, and this should complete the third video for factoring. Thank you.